So, Kepler has 3 laws also, which is pretty good to remember because Newton also had 3 laws. They're different. They're planetary motion laws, but the number 3 is the same. So if that helps you remember that. There are also thermodynamic laws we're going to look at. We're going to look at 3 laws there. So Kepler's 3 laws. The first law. If you know this, you're welcome to volunteer and answer, but I don't know if anybody knows off the top of their head. When you look at, for example, the sun, okay? So we know the sun is just a big star. The planets do not orbit, perfectly around the sun. Okay? Now, here's one thing we should mention, and most people have a very big misconception. They're very close to perfect circles, believe it or not. Whenever you see solar system scales and stuff, doesn't everybody always see this? You see the sun, and then you see like an orbiting planet like this, right? Yeah. It's not even close to that. It's actually much closer to a circle, believe it or not. But it's not a circle. That's the key. Again, we exaggerate it like this. This is highly exaggerated just to show that it's not a circle. Because see what I drew here? This is actually a pretty good representation of the Earth around the sun. This is what it actually looks like. But this is an ellipse. This is not a circle. This is an ellipse, but it's an ellipse that is close. It's so close to a circle that it looks like a circle. But it is very important to note that it is not. Okay? These are both ellipses. Okay, they're both ellipses, but the model that the Earth really does follow is closer to this one over here, which is a high misconception. That's not a circle, and I didn't mean to draw it like a circle. Imagine a circle that's been stretched only by a little bit. I'm talking like a tiny little bit. Like a what? Like an egg, but an egg, the problem with an egg is that each side has different concavity. The curvature over here is different from the curvature over here, right? So it's not like an egg because I don't want to make that misconception. The general shape, though, we want to remember is ellipse. Okay? Again, remember an ellipse. But this is not theoretically correct. You see this all over the place. This model right here, the Earth's orbit is not as exaggerated. It's closer to this than it is to this. Again, this is the model that it really looks like in real life, but a lot of people represent it like this because they want to make sure you know that it's an ellipse. Okay? Just so you know.
Sorry, so an ellipse is just it's a construed circle, but the concavities are still the same.
Sure, exactly. It's symmetric still, so each side has the same curvature, but it's taking a circle and just stretching it out. That's what an ellipse really is. Okay, take a circle and just stretch the ends. It's like the Earth. The Earth is not a perfect sphere. We call it an oblate spheroid. Oblate just means stretched at the poles. So the Earth is not a perfect sphere. It's a little bit stretched. So an Earth is really like a 3-dimensional ellipse, which is then called an ellipsoid. But we call it an oblate spheroid because it's so close to a perfect sphere, but it's just oblate on the ends. So this path here is really so close to a circle, but we actually call it an ellipse. Okay? Now, the simple way to think about an ellipse is this. Here's a circle. Whoops.
That's not a circle.
Let's just do this. Got shapes, I might as well use them. Okay, there's a circle.
Pretty good. Oh, because you used the tool.
It's pretty, yeah, I did it by hand, kid.
That's what he drew. I was like, oh my god, thanks, SpongeBob.
So, this one has a center, right? And from the center, what do we call that distance? A radius, okay? So we always have center to radius, we call that R. But here, what are they called? Focal points. Imagine if you took the center, which was here, and started making it so that it's equidistant in all directions here. These are called focal points. One of these happens to be the sun. Okay, then here's your planet going around like this. Okay? This other focal point is just empty space. And the way you can define an ellipse is by its major and minor axis. The minor axis is this distance here. The major axis is this distance here. It's like having a diameter that is changing. Okay? The diameter in the vertical direction, aka the minor axis, is this distance. We'll call this x, or we'll call it y since we're going up and down. The distance across, which is like a diameter that's been stretched, is called your major axis. For this case, we'll call it x. It doesn't matter. But again, just so you know the general geometry of an ellipse, there is not just a radius. It's like you took the radius that would be in the middle here, where these two intersect, and you spread the radius out. Okay? Again, you spread the focal point out or the center out. So does the sun have a focal point? What do you think? In this case, it X's, right? Just look by inspection.
So what is it called?
Okay, the one that's longer is called the major axis, and the one that's shorter is called the minor axis. Okay, so in this case, we'll call X the major and Y the minor. And it could switch. If you have an ellipse that looks like this, then the minor is across, and the minor is now X, and the major is now Y. Just look, which one's bigger? The bigger one is X, that's called the major. Smaller is Y, that's called the minor. You had a question, and then you had a question.
You can't just find the middle of the ellipse and make that radius.
You can, but then wouldn't the radius be changing constantly? Watch. If this is the center, from here to here is one distance, right? Then isn't that longer? Isn't that even longer? Isn't that even longer? So it's a radius that's a function of its position. So it would be like R of t. As it changes over time, the radius gets bigger. Then the radius gets smaller. Then the radius gets bigger. Then it starts to get smaller. Okay? So this, if you want to call it a radius, you can, but then you have to involve calculus, and you have to start looking at, okay, well, if I want to see the distance between these 2 points, it's called a derivative. And you can find that minimum. Then you could find the maximum using a derivative.
Yeah, right.
So it gets more complicated,
An application.
and it's more difficult than it needs to be. By simply calling it a major and a minor, it's a lot easier. Hold on, start a question, then you.
So what do you see about the sun?
The sun occurs at one of the focal points, and the planet orbits the sun, right? Well, what's the other focal point? It's empty space. So this is the sun right here, and this is empty space. This is something that's good to know, simply because most people think focal points exist as two objects, but in this case, one of those objects, or sorry, one of those locations is not an object. It's just empty space. Okay? Focal, F-O-C-A-L. We got Kenny first, actually, then Elizabeth, then Terrence. Sorry, in that order.
Remember, right? I was wondering what is the equation to?
It's like a circle. Okay, so a circle is x squared minus y squared plus y squared equals r squared. An ellipse is this is really x minus h, and this is really y minus k, but assuming it's at the origin. This is x minus h squared over a plus y minus k squared over b equals some constant squared.
Is A, B the focal points?
A and B have to do with how long the major and minor axes are. Okay, if you're dividing by a bigger number, you're looking at the minor axis. If you're dividing by a smaller number, you're looking at the major axis. Okay? So in this case, we don't know which is which, but this is a circle, this is an ellipse down here. You guys do not need to know these two. Again, Kenny just asked a side note, please. You don't need to know this for now. I'm going to leave it up here, though. Okay? For some that are in calculus, these are good to know. This is a circle, this is an ellipse. These are just geometrical shapes. Okay? But you're not going to use that here. Planetary motion? Yeah, so like this is like studying the planets movement, or like
It's like
you take
astronomy
this.
and physics.
Yeah, you're looking at like astrophysics. Astronomy, physics. Astrophysics. But yeah, I mean, there's a lot more to it. I'm giving you guys the basics. Very
I
basic.
don't like.
All right. So this is Kepler's first law, that the planetary motion is an ellipse. Elizabeth, then Terrence.
So when you told us to read yesterday
On black
the
holes?
hole, is that why you wanted us to read about the black hole? Because
I just thought it was really interesting. I read it last year, and I had students read it, and some people really liked it. So I thought it might be something you might find. It's only one page. But yeah, it does go on to this. And we're going to talk about black holes. We will. Terrence?
Because Schneider was talking about the sun, I was thinking, I wasn't sure. Is it called the ellipse? Because that's what sun is called. Because you know the eclipse, like
Oh.
the sun and the.
I didn't even think about that. Eclipse versus ellipse, why they're the same and there's both sun. Anybody Latin and Greek here? Eclipse. What's the root for eclipse? The word.
Eclipse.
Like the question is, the sun, the path of the orbit is an ellipse, and you have an eclipse. Those words are similar. Do they have any correlation?
Eclo.
No. No. Oh, I heard
like he's selling it to make profit.
My man, here. This is just like this because of the eclipse. I thought that was
And solar.
like you don't have an ear, so I guess it's like what?
And then the 100 gig.
Well, you probably like the dance on
I don't think there's any relation because I searched the article on eclipse, and eclipse is not even mentioned the whole.
Wikipedia is
But
not reliable.
it's interesting.
Yeah, it is.
It is.
For math and science, it's a very good source.
Oh my God.
I told you guys that many times. I really do. It's really phenomenal. I mean, the information they have on here is great.
What happened? Then why don't teachers get the...
We gotta keep on focus. I can't. I can talk about that forever. Let's start.
You gotta use Wikipedia to start off.
Okay, guys, focus now. So, first law is that it's an ellipse, okay? And remember that the sun is a focal point. Sun is one focal point. The other one is empty space. Okay? Now, you can read it, but do you know what it means there, sir? Okay?
Like this, like you know how like the eclipse you have a line, and then a planet moves against another line.
Okay, so here's the second law. It's like I was giving us. Here's the sun right here. Okay? Here's the planet at time 1. Here's the planet at time 2.
So that distance from the sun is the same as I think it's hold up.
Don't tell me something wrong.
Let me help, okay? Imagine, if you will.
Huh?
Imagine.
I just know it goes faster when it's closer to the sun.
It does. That's exactly right. All right. So let's go through this. Here's the sun. Here's the sun. You have, there are several reasons for it, but I'm going to go into more detail now. Here's the sun. You have an area here after a certain time passes. So let's say this is at time equals 0, and this is at time equals 8. Okay? I'm going to leave units blank for now. So let's say 8 minutes or 8 seconds or 8 hours pass by or 8 days or 8 years, whatever it may be. I'm leaving it blank for now. Okay? For something like, can you please stop? For something like this, it doesn't matter what the units are. Now, Richard, same thing, please. Come on. You don't help each other out there, you know that. So here, we have an area here. If the same amount of time passes, the areas are identical. If the same amount of time passes, the area, that's what you're trying to say, but it's tough to say that. So this might be like time equals 24 seconds, then this must be time equals 32. Okay? So it looks like the areas are different, but the idea is that in 8 units of time, the areas must be the same if they sweep out the same time. Okay? So again, after 8 units of time, this area, calling this area 2 over here in blue, and we'll call this area 1 in green, those are equal to each other. Okay? Again, whenever the same amount of time goes by, the same amount of area is swept out. We call it being swept out. So, a correlation from that is what Israel then said. This planet, if it moves this far, look how far it moves. Look at that arc length. And then look how small this arc length is. It took the same time, so it must be moving faster over here. Again, for this planet to move, we'll call this arc length A, call this little arc length B. We clearly know that the arc length A is bigger than the arc length B. Again, this is a longer arc length than this is right here, just by inspection. Now, if it travels a longer distance in the same amount of time, it must have a higher velocity or speed. Okay? Again, this is the distance traveled over 8 seconds. This is the distance traveled over 8 seconds. Well, distance over time, that means that the velocity in region 1 is greater than the velocity in region 2. Okay, these are the correlations and circles that you really want to make here. The areas are identical, but this one travels further. Look how far it goes compared to this one. If it travels further in the same amount of time, it must be going faster. Again, it travels further in the same amount of time, it's got to be going faster. For this, take this, it's over notes, you have 10 minutes. Okay? You can take it right there, it doesn't matter. For the second law, for the correlation, again, the area is the main thing, but this is the result that we come up with, the velocities, okay? Again, the area part is identical, but the key is to note that the velocity is actually faster. Not by much, though, again, because the real path of this is really like a circle almost. Again, remember I was showing you earlier? It's so close to a circle that you barely can tell the difference here. And obviously we can't feel the difference.
Is there ever the velocities will be equal, except like what would be the same space, or the same?
Yeah, from right here to right here for sure. The average velocity, slow, 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 fast, 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 slow, 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 slow. See how it's symmetric? It would be going slow in this region and slow in this region, fast in this region, fast in this. So from A to B, if A were, or A and B being an interval, if A were here and B were here, that time period, this velocity would be the same as this velocity.
Would there ever be any other situation?
Sure, any symmetric point. So at instantaneous velocity, if you're talking about, right here, same velocity as right here. Right here is the same velocity as right here. Think about it logically, right? Because it's symmetric. Isn't each half of this the same? And this is the only thing on the left. So only vertical symmetry here. Okay? Well, it would be called horizontal symmetry, but only vertical points would be symmetric. Obviously.
I'm confused. You said there's horizontal symmetry, so...
Yeah, because look at this, right? There's horizontal symmetry, and the sun happens to be here, so it's the same on this half as this half, but it wouldn't be the same, Houston, on this half as it is on this half, because the sun's over here, right?
Right, that's what I was saying. You start
So-
putting that.
So the symmetry is this, right here. That's why this, at this point in time, the velocity would be the same as this point in time. Here, it'd be the same as here. Here, the velocity is the same as here.
Oh, alright.
Here is the same as here, and so forth and so on, until it gets to its max velocity right here. And then it gets to a minimum velocity when it's furthest away.
How do you know? Oh, because that's the point.
Well, we just made the correlation, right? The further away it is, the lower the velocity. That was what we're saying here.
Yeah.
So here, this would be the min velocity, minimum velocity. This would be the maximum velocity. Okay, because the distance from the sun to the point is a minimum here. This is the minimum distance. From this point on, the distance gets bigger, bigger, bigger. Then the distance is even bigger, bigger distance, furthest distance. Furthest distance away is the slowest velocity. Closest distance over here is the highest velocity. You're maximizing velocity while you're minimizing the distance. You're minimizing the velocity while you maximize or get the biggest distance. Okay, they're opposite of each other there. And I know at pre-calc you guys already started talking at local extrema, like local mins and local maxes. This would be, you should have by now.
No, we're like...
Thank you. Now, please guys, stop. You did. I talked to Mr. Smith about this. This would be your global max velocity. This would be your global max velocity. This would be your global min. There are no locals in this kind of a problem, okay? These are just globals here. Yeah.
And it's like,
We're looking at the distance, okay? Because if I did the displacement is this line here. The displacement between these 2 points is that line right there. We're looking at the distance traveled. Okay?
That's why I was looking at negative.
No, but we're just looking at as if this is the starting point and this is the final point. It's a positive net growth. Because it's like, you know what I mean? Which way would be negative, which way would be positive? Clockwise, counterclockwise?
Well, you have X and Y.
I get it, but the distance traveled is an arc length. That has nothing to do with X and Y being negative, positive. It's from here to here. How far does that path take? What is the length of the curve? Okay, so the second law again. The second law is this. The areas that it sweeps out are identical during the same time periods. So after 8 minutes, it'll sweep out the same as here in 8 minutes. The shapes look different, but the areas are identical. And that leads us to the conclusion that the velocity is bigger. The velocity is bigger when it's closer to the sun. The velocity is less when it's further from the sun. Okay, that's the second law there. Second law. Third law.
I was asking. I mean, you could have recovered it when you like covered it.
So you said the areas are identical.
Yes, the swept out areas are the same during the same time periods.
He's not going to advance on my comprehension.
What do you mean by?
Can
you repeat that again?
It's like every 8 years?
This is a swept out area. That area that I'm coloring in is equal to that area here that I'm coloring in because it took 8 minutes to go here and it took 8 minutes to go here. Okay? It does not matter what the shapes are, guys. What did I say exact wording for you? Because I'm going to say it differently, guys. I'm not reading this. I'm coming up with it every time.
I just put the areas are identical of the swept area at the same time when the time was the same.
During the same time period. The area swept out will be the same if the time period is the same. And that's what we're saying. Guys, you don't need to write words all the time. That's why I did image here. This image tells a lot more than words do, okay? Swept out areas are the same if the time interval is the same. Okay. The third law is very confusing in words. I'm not even going to go into the words of it. And I heard it say, I'll read it a minute ago. Okay? It talks about squares of proportional orbits and stuff. I'm going to give you the equation that comes about from it. What's really important. Okay? The orbital period, T. Okay? Orbital period. So, for example, that's what I'm telling you. Don't read what you see on there. Listen to what I'm telling you. Orbital period is like, for example, for the Earth, what's the orbital period that we revolve around the Sun for? A year. No, that's rotating, revolving. 365.246 days. Is that little decimal at the end? That's what gives us the leap year this year? We have a leap year this year?
Yeah.
Okay. Every 100 years, though, we have a no leap year twice in a row. Did you notice that? Because it's not, if the year were this, if this were the year here, then every 4 years we'd have a leap year. But a year is really, oops, it's like 254 or 246. It's 4 off, I know that. It's either 254 or 246. I forget if it's 4 above or 4 below. But this is the actual year. So every 100 years, we skip a leap year, actually, because of that. Which is pretty interesting to think about. Every 4 years a leap year, but every 100 years, you ignore the leap year. And that's what takes account in that one little decimal. Yes, because of the fact that the revolutionary period or the orbital period of the Earth is not 365, but 365 and a quarter. The quarter is why you have a leap year every 4 years.
That's revolving. And what's the 24 hours?
Rotating.
That sucks. You know what?
Now,
I think it's for me. That's the radical.
just ask Maria this about. Maria, watch the last 10 minutes of the video. That's right now. All right. Now, the equation we're going to use here is important because remember how a minute ago we talked about r as the distance between the two objects? Okay. If we look, and you got to think logically right now, look back at the shape of the path. This distance is one distance, right? And then this distance is a whole other distance. So from here to here, we're talking, let's say, just hypothetically, say this is 10. If that were 10 whatever, this would be like 30 or 40 or something, right? So do you see how the distance between the Earth and the center point that it's centering around changes? Okay, this is a short distance and this is a long distance. So the problem here is that r is not really just the distance. We call it the mean radius. Mean radius, which is really what Bridget was talking about earlier, where why can't we just find the radius from the middle? If we found the radius at every location and took the average of them, that's what this is right now.
So it's like adding the two radiuses.
It's like adding all the radiuses, or all the radii around the whole circle, all those distances up, and dividing by however many there
Is that
are.
a constant?
It's a constant, yes. Everything has a constant.
Now we make up a number.
Okay? So for example, the Earth has a mean radius that it is away from the Sun, an average distance from the Sun. It changes throughout the year, but for an average, it's the same distance around the Sun. That's what we're looking at.
So what about the other focal point?
We're not even worried about the. It's the same. It's symmetric. So if you did it on that side, you'd get the same answer.
Okay. I mean, yeah, I figured that. But
Just the symmetry is what allows us to do that. What is G, everybody, again? 6, 7, 10, and negative 11.
Whatever you care is not straight.
So are you gonna go with R?
Oh, 6, 6, 7.
You said wood, but you're trying to make it. You asked her what was higher security. I did not ask her, I said where. I'm just so mad at you.
M. Now, this is the really important part. If an object is revolving, it has a mass. But we don't care about that object's mass. Again, so imagine, for example, a satellite above the Earth. So your cell phone, you send a signal to the satellite, it gets sent to somebody else. That satellite that's rotating, its mass has no effect on it. You can put any object up there with any mass. It makes no difference. It's the mass of the central object that matters here. Okay, it's the mass of the central object that determines how long it will take to revolve. So it's the Earth that takes the time. Okay, it's the Earth that's important.
So satellites orbit, right?
Correct.
So you said cell phone send a message. So if right now I send a message, right, and the satellite just happens to be right over the top, would the message be sent quicker than if the satellite was on the orbit on the other side?
Here's something that most people don't know. Satellites move with the Earth. They're called geosynchronous. So for example, imagine there's a satellite right above me right now. As the Earth rotates a little bit, because the Earth rotates once every 24 hours, as the Earth rotates, the satellite moves with you.
So, but if I was over there,
It's moving with you. Oh, well, sorry, if you start running somewhere and stuff, that's totally different, sure. But the distance you run is so insignificant compared to the distance away you are that it would have no effect whatsoever. But satellites are traditionally geosynchronous. They move with the rotation of the Earth. So the satellite that's always above Washington, D.C. for cell phone reception or whatever it may be is the same one that's always going to be there. And it's not like we're rotating, we're getting a different satellite every once in a while. Every 24 hours it rotates once. So if you want to think about it that way, every light is 360 degrees in a circle. We divide that by 12, we get 30. 30 degrees every 2 hours. So 15, every hour that goes by, the Earth rotates 15 degrees, 15 degrees, 15 degrees every hour. So you can find the angular velocity if you know it's 15 degrees per hour. Okay, so we are moving. It's just that we're moving with the Earth. We're on the Earth and it's moving us with them, so we don't feel it or hurt it, whatever. Either one though. So, again, M, remember, M is the central object, not the satellite. So for example, the Earth is really a satellite of the sun, because we revolve around the sun. The moon is a satellite of the Earth. So everything is really a satellite somewhere or another, okay? Until you get to really, deep thinking in astrophysics, which we're not going to talk right now. Okay? But everything is going to be really revolving around something, 2 pi, constant. G is our constant. Remember, G, what did I tell you yesterday? 6, 6, 7, 10 to the negative 11. Okay? Remember, 6, 6, 7, 10, negative 11. Times 10 to the negative 11.
You made that so much better.
Okay, the second part of the third law, there are 2 parts. And you don't have to memorize these formulas. So the third law, you really don't have to memorize. Whoops.
Wait, you never gave us R.
I'm going on.
That's what we're trying.
No, R is the mean.
R is the mean radius. What do you mean?
You said it was a constant.
Depending on where okay, if it's something that's going around the Earth, what's the distance? If it's something going around Jupiter, guys, don't worry, relax. Look at all the different ones, depending on where you are. If you have a satellite going around the Earth, that's going to be a different distance than a satellite going around Jupiter, which is a different distance than the Earth going around the Sun. So it's not the same for everything, it's specific to every scenario. Okay? That's why you're going to be given it. It's a constant, but based on the scenario. Third part, the velocity of the object is gm over r. Same variables, okay? M is still the mass of the central object, so you can draw another arrow here if you'd like. R is still the mean radius, okay? The mean radius of the object in motion, again, how could you have the... Okay, I get what you're saying, Andy, the radius of the Earth, no. The radius of, for example, the center of the Earth to the satellite, whatever that distance is.
You said GM over R?
GM over R, okay? GM over R.
G and then.
It doesn't matter. If you write it as GM over R, it's the same thing, people. It's the same thing.
You like coefficient.
Yes, and G is a constant always, right? So I'm thinking of this as a constant coefficient. That's exactly why I did that.
So 1/2.
The what? The 1/2 instead of over 2, yes. Remember, guys, this is the velocity of the object. Now, before we end today, what I want to do is go over a scenario that is very misleading. Very misleading. Come on, guys, you gotta write a little faster. I wrote like 3 letters there. You telling me you didn't write that? I literally wrote 4 letters. I'm sorry, 4 letters in a radical sign.
No, 2 symbols. Equal sign.
And if we're really being careful, 2 arrows also. It's not a lot. I'm just saying, please keep up. Please keep up. Now, for the next thing we want to look at here, and this is a little bit confusing. I'm going to explain this why. If you have the Earth here, and you had an object that was, let's say, a satellite in orbit around the Earth. A satellite is always depicted as like a bow tie, in case you're wondering. Any representation with engineering? You put a bow tie.
Cylinders like a ball, and there's like.
I would have thought you were
You're
like,
no, that's what I
The TIE fighter.
I thought it would be like that.
And the Death Star.
That does look like one of the fighters in Star Wars.
And don't forget the little
Never
boy.
mind.
Either way, it's the bows on the outside. They represent the satellite names.
What idiot.
All right.
I just like how it was all.
Okay? Now, here's the very important part here. If you have the radius of the Earth, that's not the actual distance away. That's not the mean radius. Remember, the radius of the Earth is RE, right? That's that distance right there? But the actual distance also has to include what? Whatever the elevation is in space. Very good.
Oh, like the
Okay.
mountain station.
Yes, very good, like we talked about the other day. Okay, like having a mountain that's 1,000 kilometers. So, if you had a problem where it said find the altitude above the Earth of a geosynchronous satellite, you're finding this distance right here. You can call it whatever you want. What do you want to call it, guys?
R.
H for height? H works for me as long as we have a reason. Okay? H. So, if you're looking at a problem where you have a satellite going around the Earth and you want to find the orbital period, you're going to use 2 pi times square root, was it GM over R? Okay. Of G times the mass of the Earth over.
It's R cubed over
It's
GM.
R cubed over GM.
Thank you. The other one was GM over R.
That was the second one, but there's no 2 pi.
Like I lose my pen.
R cubed over GM. Now, the question becomes this. For this example, we're looking at a satellite. The central object is the Earth. So we call that ME. Again, the central object is the Earth. We're looking for the orbit period of a satellite. Now, what is it?
REH.
Not REH. You're making a little mistake there.
RH.
No. You're close, Kenny. Kenny was the
What did you
closest.
say?
He said REH cubed.
Where?
What is it?
RE plus it.
RE plus H cubed. Now, let's go over this. Let's explain why. The actual distance, remember segment addition postulate from geometry?
Yeah.
The segment from
That one
here
actually I remember.
to here,
What happened is argument.
this is the distance we're looking for.
What's it?
I fell off the wall the other day, so it's over there somewhere. Okay, guys, turn this way, please. Come on. Here, we're trying to find out what the mean radius is. The distance between the satellite and the center of the Earth is what always goes here. The satellite and the center of the planet. So here, it's not a distance of RE, which is the radius of the Earth, but it's the radius of the Earth plus H. So we have to put those together first and then cube it. Okay? Orbital period, T. Orbital period.
Make it O. What does T have to do with O and
Is it 1201 the period or 1204? Okay.
whatever comes?
So here's what I want you to do this weekend. You know what? Just take off the weekend.
Yeah.
Because I feel like
wrong with that? They give me the work on the tell me what's wrong.
Guys, get caught up on other work, because next week we have a lot to do. This is one of the last topics, just so you know, one of the last topics for this chapter. So toward the end of next week, we're looking at around test time, okay? So next week, make sure you get your stuff done.
English.
Oh my God.
Probably don't have
Paper
We have English test
end of the
on
world.
Tuesday.
I'll see what I can do, guys, but for now.